All right, good. So for our second talk for today, I'm happy to introduce Sophie Huiberts. Sophie is a Simons Junior Fellow at Columbia University in New York. And before that, she completed her PhD at CWI in Amsterdam, working on analyzing algorithms like the simplex algorithm for linear programming and branch and bound for mixed integer programming, and questions about convex polyhedra. And I think she's going to tell us about some recent results in that space today. So Sophie, welcome and take it away.
Yes, thanks everyone for being here, and thanks to the organizers for putting together this wonderful seminar series. Yes, so to start, a long time ago in a land far away from here, I was taking this 3-day course, and it was a course that was taught by actors. And they told me about sort of things about like storytelling. And one of the things that I learned about is this story structure. It's called the hero's journey. So this is like it's a motif that fits many stories, new and old, from different cultures. Beowulf, Moby Dick, Star Wars, you name it. And all these stories, they start out by us meeting a hero in their comfortable environment. When something happens, some inciting incident occurs, and a call to adventure finds them. After initially refusing, the hero will take up the quest and cross the threshold into the unknown. There they face challenges, they might meet a mentor, and at the climax of the story, there is a revelation, there is a literal or metaphorical death and rebirth. Then there is a phase of transformation. Either the hero transforms, the situation transforms, an object transforms. There is a scene that's called Atonement. Here, the hero might reflect on their actions, grow as a person, overcome a barrier. And after all this, they return back home, but maybe their home has changed. They have changed in profound ways that really have this journey, leave a mark. And so what I learned is that this template here fits many works of fiction, but actually this same story structure also fits well this talk actually. So let's meet our heroes. Our heroes are 3 definitions. They are going to be the diameter of polyhedra, going to be polar duality, and random polyhedra. And I'm going to go through these step by step. So the diameter of a polyhedron is an integer number that answers the following question. If I have any 2 vertices of my polyhedron, how many edges do I need to connect them together? How many edges do I need to traverse to go from any vertex to any other? For example, for this 3-dimensional cube, I can connect the top and the bottom vertex using 3 edges, and 3 is the diameter of the cube. And so this is a mathematical definition, right? But this is, in fact, like the algorithmic version of this question is something that we all know and love. It is the simplex method, where we are given a vertex of a set. It's given by these linear inequalities, and we wonder how many pivot steps do I need to take to find a vertex maximizing a linear objective. So these two questions are like intimately related to each other. And as such, people have thought about this question of diameter for a long time. Back in the 50s already, Hirsch famously asked, if I have a polyhedron in Rn with m facets, is the diameter at most m minus n? And if you just go out into the world, you find a polytope lying around and you measure it, this is probably going to be true. But as it turns out, the conjecture is false. An unbounded counterexample was constructed by Klee and Walkup in the 60s. And more recently, in 2012, by Santos, a bounded counterexample was found. But still, the question of what kind of upper bounds can we give on the diameter is an open problem in the sort of theory of linear programming. What we do know is two different upper bounds. One is from work by Barnett and Larman, stating that the diameter of a polytope of a polyhedron like this is at most 2 to the n minus 2 times m. And work initially started by Kalai and Kleitman, but refined by others, states that the diameter grows at most as roughly like m to the power log n. Our second hero definition we find sitting in a bar somewhere is polar duality. Another definition. So given a convex set P, I'm going to define P polar as the set of all the x's in Rn, such that y transpose x, this inner product, is at most 1 for every y in P. Now, there are a few reasons why this is a nice definition. For example, if P is a bounded polytope that contains the origin in its interior, then P polar is a bounded polytope that contains the origin in its interior. We know that the polar of P polar is equal to P. If P is simple, then P is simplicial. And in ways you can sort of think about these two objects as relating to each other, like where P is your primal object, P polar is going to be your dual object. And this is, a lot of these ideas go back a very long time. So this is a figure from the 1600s from a book by Kepler, illustrating that the infinity ball and the one ball are dual to each other in this way. And this is not just a definition that you get from like whatever sort of weird linear algebra. There is also, this is also, there you get a relation between the faces of the two polytopes. The facets of P will correspond to the vertices of P polar, and the other way around. The edges of P will correspond to the ridges of P polar, and the other way around. All in all, there is a lot of rich structure going on here. Our third and final definition is random polytopes, the thing that we're actually here to study. So what I'm going to do is I'm going to randomly sample a set A of unit vectors sampled from the sphere. Technically speaking, they're going to be drawn from a Poisson point process. If you're not really familiar with what that is, think of me just sampling independent IID uniformly distributed vectors from the ball. And from the set A, I'm going to define two polytopes. One is the set P, polytope P, all the x's such that A transpose X is at most 1 for every A in A. And the other is the convex hull of A. And just to sort of give you one sort of sample from this distribution, here in the picture you see one sample of P in 3 dimensions with, I don't know, like 50 or 100 or so inequalities. And as these things go, so we have seen our definitions in their places of comfort, and something happens. And for us, the inciting incident is this line of work by different people. And we can sort of summarize this as saying that if I have a polyhedron given by inequalities AX at most P, if the matrix A is all integers and every square submatrix has determinant of absolute value at most delta, then the diameter of this polyhedron is bounded by a polynomial in n and delta. How to think about this is, roughly speaking, that this subdeterminant condition says something about being well conditioned, being nice. So really sort of the way to interpret this is if a polytope is nice, then it has small diameter. And people like to think, like theoreticians, people working in random geometry, like to think that random objects are going to be well conditioned on average. They're also going to be nice in their own little way. So maybe there's something here. Maybe we can prove something in terms of an upper bound on the diameter. And in fact, there is even more evidence to sort of point us on this quest, which is the work of Borgward. Borgward, he made a big study about the average case analysis of the simplex method. He wrote a very thick, complicated book about this. One of his sort of key theorems that he proves is the following. If I have a orthogonal projection pi onto a two-dimensional subspace W, then I can plug my polytope P into pi and get a random polygon, a two-dimensional object. And what Borgward did is he counted how many vertices this object has. To sort of illustrate this, so here we have a picture of a polyhedron that's projected onto the screen, the two-dimensional screen, and Borgward would be counting how many vertices there are on the boundary of this picture. And what he noticed, what Borgward noticed, is that in fact, if I have two of these vertices on the boundary, they're going to be connected by a path consisting of edges on the boundary. And in particular, any two vertices that project onto the boundary of pi of p are going to be connected by a path of length order n squared m to the 1 over n minus 1. So for this size, we actually have like Borgward found like lower and upper bounds. And this might already sort of be a very big clue on what the diameter of random polyhedra might be. And Borgward actually asked this question like, hey, can this, like, is there some diameter result to be expected here? So this is exactly going to be our quest. With my P and my Q as defined earlier, let's say that we're going to have exponentially many constraints. Then what we're going to be proving is that with very high probability, we have lower and upper bounds on the diameters of both Q and P. So diameter of P will be at least n times m to the 1 over n minus 1, at most n squared m to the 1 over n minus 1 plus 2 to the order n. And pretty much the same bounds for Q, but now with one factor of dimension smaller, both. So our heroes have a quest. They set out into the unknown. They face all these challenges, but they will meet a mentor that will set them on their way. They will teach them the forest. They will point them what direction to walk towards Mount Doom. And our mentor is a lemma. Just as every story beat is actually going to be a lemma or a theorem. So the lemma is as follows. If I have a bounded simple polytope P, and I have this P polar, then the diameter of P is lower bounded by n minus 1 times the diameter of P polar minus 2. Proving this is slightly non-trivial, but if you honestly, like, if you think about it for a half an hour, this you will probably get there. But due to time constraints, we're not going to prove it today. So, but what this lemma really does for us is that now if we want to prove all of our 4 results, 2 lower bounds, 2 upper bounds, the only thing that is left to do is prove an upper bound on the diameter of P and a lower bound on the diameter of P polar. Then we just get the sort of sequence and we get all the results that we want. Our mentor really sort of cut our work in half here. Now, the climax of the story. We're going to start with a definition. I'm going to call a set of unit vectors, B. I'm going to call this set epsilon dense for some positive epsilon if every spherical cap of radius epsilon contains a point from B. What's that mean? Think of a spherical cap as just being like a little ball drawn on the surface of the sphere. Or like you could alternatively formulate this definition as B is epsilon dense if for every other unit vector there is a point in B that is a distance at most epsilon. Now I can put on my calculation hat, I can find my integral solving jacket, and just calculate the probabilities, and I can find that our random set A is going to be epsilon dense with overwhelming probability for epsilon being roughly log m over m to the power 1 over n minus 1. So A is going to be dense. What next? Another sort of conclusion we get from that is that every facet of Q, the convex hull of A, I'm going to say is encapsulated in a spherical cap of radius epsilon. That's a lot of words. So here is my sphere, my unit sphere. And on it, I drew in purple, I drew one facet of Q. Now, if it's a facet of Q, then what's it mean to be a facet of a convex hull? It means that there is an affine subspace that supports this, where this facet lies inside, and where all the rest of Q lies on one side. In this case, though, the rest of Q will be below the hyperplane. And the subspace is going to intersect the ball in a little circle. And so what I'm actually saying here is that this little circle cut out is going to have radius smaller than epsilon. Because if it was bigger than epsilon, then by the sort of definition of epsilon denseness, we would find a point A, which is a vertex of Q. I would find one both above and below the hyperplane, which contradicts the whole facet situation. So that means that every facet of Q will have small radius. In particular, every edge of Q will have length at most 2 times epsilon. But now we're kind of in business, because our convex hull Q will also have vertices that are far away from each other, a distance at least 1. Because I'm sampling vertices from the sphere, there's going to be some on the North Pole, there's going to be some on the South Pole. But what happens now is that I want to connect 2 vertices that are distance 1 apart, but every sort of step, every individual step will have length at most 2 times epsilon. So I'm going to need at least 1 over 2 times epsilon many steps. If you take short steps, you have to cross a large distance, you're going to need to take a lot of steps. And the lower bound that we get, it's omega of m over log m to the power 1 over n minus 1. Now, you might say, okay, we have some result, but this lower bound that we have now spent all this time on is not actually optimal. So inside, we kind of die from embarrassment. This is the death phase. But we have some results, I guess. So that's the being reborn part. Thinking back to our story structure, the next phase is going to be a transformation. And what's going to transform is our lower bound, and it's going to magically transform into an upper bound on the diameter. So what we've seen last slide, what we've learned, is that with super high probability, all my facets are going to be small, are going to have small diameter. Which means that if I talk about facets or edges over here and facets or edges over here, if that's far enough apart, then these events are going to be independent random variables, like almost independent. But this is good, because I have my polygon pi of p, and I'm going to just sort of look at how many edges does it have. How many edges does it have here? How many does it have here? How many edges does it have here? And if I consider all of these sort of short little segments, each of small enough length, then Borgward has actually computed the sum of these independent random variables. So we're kind of in business here, because we have a sum of independent, nearly independent random variables. We know upper and lower bounds on their expectation. Ring, ring. Who's that? That's Mr. Chernoff. Chernoff has this concentration result, and that will in fact sort of tell us the following. That's this projected polygon pi of p will have at most n squared m to the 1 over n minus 1 plus 2 to the order n, many vertices with tremendously high probability. And so from here to get an upper bound, like it's gonna take a bit more legwork, but what you can sort of do is you can consider many of these different projections pi onto different two-dimensional subspaces, and take a union bound. Because we have such high probability, we can take a union bound somewhere, and we can sort of extend this result into an actual upper bound on the diameter. As our last step in our journey, we have to face up to our sins. We have to grow as a person. And what it will mean to face up to our actions is we're going to have to find an actual lower bound. And the lower bounds, so let me roughly sketch how the lower bound, the actual lower bound on the diameter is going to work. So let's consider Q, the convex hull of my point set. And I want to prove that it has large diameter. So what I'm first going to tell you is that if we both know of a given polytope, and if I have a path on this polytope and I want to communicate it to you, well, what I can do is I can give you a curve of objectives. I can give you like sort of a line, a curvy line of objectives, and you can extract my path by looking with what vertices are optimized by different objectives from this line segment, from this curvy curve, and you can recover my path that way. So every path on Q can be described by a curve of objectives. And what I'm going to claim is that if I have one curve that connects two antipodal points, the North Pole and the South Pole of the sort of sphere of objectives, it's going to meet m to the 1 over n minus 1 distinct vertices of Q with high probability. So this is just talking about one curve. So here is my sphere of objectives. There is one curve in purple. And how you argue this, and also actually where this number m to the 1 over n minus 1 comes from in the first place, is that if I have my curve and I'm going to put like little sort of spherical caps along the curve, I'm going to put m to the 1 over n minus 1 equally sized of these little caps. Then with my calculation hat on and my integral jacket on, I can calculate that every one of these caps will contain a point from Q with constant probability. But because they are all disjoint sets, these are all independent random variables, I have my standard concentration results, and I'll find that if you sort of work through what it means to like optimize a point and whatever, you're going to find that this curve will meet this many vertices of Q with high probability. And now what we ideally want is we want to take the union bound over all curves on the sphere. Of course, there are going to be uncountably many of these, so you need to like find some way to discretize the set of curves, take union bound over all the options, and maybe slightly surprisingly, the numbers will work out and you will actually sort of get that things are going to work with high probability. And this is going to get you a lower bound. So we have gone through all these phases in the unknown, and we return back home forever changed. And as it goes with adventures, like we might have found some answers, but perhaps we've found even more questions that are still unanswered. I'm going to leave you with 3 of them. One is, can we close this gap between the lower bound and the upper bound? What happens for other distributions, which might be slightly more difficult to analyze, like if points in A are drawn from a Gaussian distribution? And what if I don't have exponentially many points, but only polynomially many? What happens then? I'll leave you with this. Thank you all so much.
All right. Thank you very much, Sophie. So I think we have time maybe for a question from the audience before we break out into the breakout rooms. Any questions? Okay, the talk was perfectly clear, and you already left us with 3 questions. So then, in the interest of time, I suggest maybe we stick around for the social part of the seminar, if you'd like, and we'll break out into 2 rooms where the speakers will be available to discuss some more, or not discuss the talks also.